This is video number 5 in my fastbook-benchmark video series, and in this video I'm going to go over single vector search. So the key differences in what we're importing, we're going to import the F module from Torch because we're going to use cosine similarity, and everything else is pretty much the same, but now I am installing and importing sentence transformer, and I'm using the BGE small embedding model. A reminder that I have a utils.py that has all of the functions that I've created in the previous notebooks and videos, and I'm just importing that as a script or as a module because I don't want to, fill up 10 cells with all of those functions in these videos. So we're going to start, as always, by loading our data. And this will download the Jupyter notebooks. I'm then going to get my benchmark data set. It's a JSON file. I'm going to get my, actually don't need keywords here because I'm not doing full text search. So I'm going to get my data. And this is going to process the data and convert the notebooks to strings in 2 or 3 chunks each. So the first thing I need to do for single vector search is I need to embed each question into a single vector, and I need to embed each document into a single vector. So I'm going to start by grouping my questions by chapter. So I'm going to iterate through my benchmark, and I'm going to set default the chapter string, and it's going to be an empty list, and I'm going to append to that list the question text. And a small adjustment that I'm going to do here is I'm going to strip away, and let me make sure I copy the correct string. So I'm going to strip away double quotes from the text because I found that double quotes, or really any punctuation, does affect cosine similarity when it comes to the embedding space. And so I'm going to strip at least those double quotes from the questions. So this should run successfully as it does. And I'm going to now wrap this in a prep questions function. And I'm just going to grab this, dump it in there, and make sure I return questions. Okay, cool. So now I have this nifty little function that can reduce some of the code. So this groups our questions by chapter. And one thing I'm going to do is I'm just going to double check that this is got the right number of questions per chapter. So we're going to go through the items, and I'm going to print the chapter and the length of the questions, and I'm going to accumulate the number of questions as a sum, and I'm going to make sure that the sum is equal to 191. So that assertion is correct. And if you look at the dataset statistics, you can see the number of questions per chapter. So 30, 26, 31, all the way up to 24. And this is giving us the right number. Cool. So that gives us the questions in the format that we want. Now we're going to embed the questions. So for the first run, I'm just going to take chapter 1 questions and embed those. And the shape of this should be the number of questions by the embedding dimension, which is 384. So yeah, that looks good. So I have 30 questions, and now they're all embedded with one vector per question. Before I embed my data, I'm going to do some data prep. So I'm going to set my chunk size to 500 tokens. I'm going to chunk my documents with my process documents function. So it takes the first data, or first chapter's data, and Let's do, oops, let's do that. And then I'm going to assert that the length of the documents is 57 because this is something that I can check and I've ran before. And it is. Cool. So now I can embed my documents. And let me actually just copy this. And copy this. And this should be now 57 by 384. Good. So that is looking good. All right, so now I have all of my question embeddings and I have my document embeddings. And now I'm going to use the power of broadcasting to calculate the cosine similarity between each question vector and each document vector. So this was something that I found by just trial and error. But if I need to get the dimensions just right, and I'll show you what that means. And basically what I'm going to do is I'm going to add a unit act in different positions in each of these so that we can see that broadcasting will sort of fill in the blank. So my questions, I'm going to embed them as 30 by 1 by 384. And my embeddings, I'm going to embed as 1 by 57, reshape as 1 by 57 by 384. So I've added this extra unit axis to my embeddings, and we'll see that in action in just a second. So I'm going to compute cosine similarity, and I want to get the indexes of the top ranking ones. So I'm going to call cosine similarity between this one right here. So question embeddings, I'm going to unsqueeze it. And then data embeddings, I'm going to unsqueeze it as well. And this is the key. I'm going to do this cosine similarity on the second dimension. So this is a 0, 1, 2, 0, 1, 2. So it's going to run the cosine similarity in the embedding space. And then I'm going to sort by descending, so I get the top ranked values, and I'm going to take the values, which is 1. So if I run this, I'll see that my shape is in such a way that I have 30 questions and 57 documents, and that's a matrix of cosine similarity values. So the power of broadcasting in action, very cool. This was really fun to see and figure out. Okay, so that gives me the cosine similarities. And for each question, I have a cosine similarity with every single document in that chapter. So what I'm going to do is I'm going to get my top k indexes, which is going to be, let me first define top k. So top k is 10. And then I'm going to get my top k indexes, which is going to be my indexes. I want all of the questions, and then I want the top 10 or the top k values. So this should be 30 by 10. So now I have the indexes of the top 10 documents for each question. And what I'm going to do now is I want to get basically all of these in a particular shape. So let me just run this code here. So I have my row indexes for row indexes in top k indexes. And this is a bit funky, but I'm just going to show this. And so I'm iterating through top k indexes, and I'm capturing each row. And so now I have 30 of those elements. And let's just take a look at one of those. And here we go. So here is the tensor for the top 10 indexes, or the top 10 indexes for the documents for my first question. Okay, and we'll see how this comes into play in just a second. So now I'm going to get my top k chunks. And the way I'm going to do that is I'm going to say in my documents, get me the ith index or idx index. And let's make sure we do this the right way, and this is good for each index in my row for that question, and then iterate through the row indexes in my top k indexes. So this is, kind of a nested list comprehension. So I'm going through each of these rows, and there's 10 values in each row. And so for each of those values in each row, I'm indexing into my documents, and I'm pulling out the documents corresponding to these indexes. So if we look at the length of our top k chunks, this should be 30, and that's correct because I want one document for my 30. I want my top k documents for my 30 questions. And just taking a look at one of these. Okay, so we can see here, and let me do a length here, and we'll see that this is 10. Cool. And one thing I like to do is just run an assertion, and I'm going to assert that the length of 0, or length of O, is less than my top k, or less than or equal to in my top k. And that's the case. So I have now a list of documents, the actual text, that correspond to each of the questions in Chapter 1. Okay, so that is everything I need to do for one chapter. And just to recap, we embedded our questions, we embedded our documents, we processed our documents in between, so we get the chunks. And then we used broadcasting to get the cosine similarity. And this gave me 30 times 57 cosine similarities between each query and document. I pulled out the 10 documents for each question, and then using list comprehension, I pulled out the strings that actually correspond to the document at each of those indexes that were the top cosine similarities. So I can wrap this all into a function and do this for all of my chapters. So I'm going to run this line again to get my questions. Okay, so I have all my questions grouped together by chapter. And now instead of doing one chapter, I'm going to gather all of my questions embeddings into a dictionary. And I'm going to iterate through those questions that are grouped together by chapter. The questions that I need are, actually, I think that's redundant, so I don't think I need this line. So let's see if that works. So I'm going to assign to my question embeddings dictionary, and let me just grab this code from up here. This one. Okay, cool. So I'm going to embed the QS questions, and I'm going to save that here. And then I'm going to check what the shape is of this. So this should match the number of questions that I have in each chapter. So we run this, and I get 30, 26, 31, 23, 27, 20, 34. Good. So this is so far correct. I'm going to now do the same thing for my data. And then I'm also going to store all of my documents so that I can retrieve the top k chunks. So now we're going to iterate through data items. And let's copy some of the code that we ran above. So this is going to be reused. And instead of chapter 1, we're now doing all of the chapters. So I pass it text. And I'm going to grab this. So this is going to embed my documents. And in all docs, I store my documents, so the actual strings, the chunked strings. And in data embeds, I store my embeds. So let's run through this and make sure it works. Cool. So the last thing I want to do is use my cosine similarity code and run it through each chapter. So I'm going to have my final results that I'm going to put in results. And then I'm going to go through my notebook's keys to get my chapter in string values. And then let me copy and reuse some of this code. So I'm going to be calculating the cosine similarity between that chapter's questions and that chapter's data or document embeddings. I think everything else is there. I'm going to grab my top k indexes, and then I'm going to do this list comprehension to iterate through those indexes and get my top k chunks. And I'm going to do that from documents, except now I want to do it through all documents, and I'm going to specify the chapter. Okay, I think that looks good. And then I'm going to extend my results with top k chunks. I'm going to assert that the length equals 191, so I have 191 questions in total. And then for each question, I'm going to assert that the length is less than or equal to top k. And then I'm going to wrap this into a function that I will call single vector retrieval, which takes my notebooks, which takes my document chunks, it takes my document embeddings, my question embeddings, and a top k value that I'm going to specify as 10. And then this is going to return results. So if I typed everything correctly, we will check in a second if that works. So single vector retrieval, notebooks, all docs, data embeddings, question embeddings, and okay, that at least works. And then I'm going to use the score retrieval function that I developed in my last video. And so this takes the benchmark and my retrieved passages, and it calculates modified MRR and modified recall. And then the last step is I have these pre-calculated values that I did by hand. You can check out the Excel file here and the script, the notebook that ran those results here. And so these are the values that I should get with my functions. And we do. Okay, so that is end-to-end using single vector search for retrieval. And in my next video, which should be, at least for now, the last video in this series, I will run the same kind of approach, but I'll do it with the Colbert models. Awesome. So thanks for watching, and I'll see you in the next video.